This unit is going to cover physical and chemical control of microbes. A place of business, hospitals, of course, they are concerned with controlling microbes. You can't own a business like a restaurant and have mold growing in the bathroom or in the kitchen or anywhere else or any area where customers are going to be. Hospitals, of course, are worried about what are called nosocomial infections. Infections acquired while a person is in a hospital stay. Hospitals are constantly cleaning. They're constantly administering drugs. And so a lot of the microbes in a hospital are very resistant. They're upset. They're under constant bombardment. But this section is actually pretty short. It's just some really easy ways that but either physically or chemically you can use to control microbial growth. What I'm thinking of, hospitals, and you can see it over here on the right, hospitals have to sterilize instruments. If they're metal, that's pretty easy to do. But I know in my experience, I remember mouthpieces that were made of rubber that you had to sterilize between patients because you didn't give them their own mouthpiece each time. So that's what this section is dealing with. So I'm going to go down. As always, I have an outline, so we really don't have a lab book for this course. And there are some lab scenarios in this. In other words, I'm just going to take you through a couple of experiments that you would do in a microbiology lab relating to all this. So like it says here, in the medical profession and in other health-related areas, microbial growth can be controlled by physical means as heat, radiation, filtration. And there are some chemical as well. We're going to talk physically first, and then we'll go to the chemical part. So things you have to consider: the type of object to be treated. Not everything can be heated. Rubber will melt. That's what that's referring to. Sometimes rubber is actually gassed in a chamber to sterilize. The quantity of materials to be treated, you have to consider that when you're trying to sterilize anything. The type of microbe to be controlled. One of my last jobs, it was a tuberculosis hospital, and Mycobacterium tuberculosis has a waxy cell wall, so these two kind of go together. And it's harder to kill, and it can last for long periods on the floor without drying out. And so if you know that beforehand, you're going to use a different kind of method to clean those areas. And then anything that's a spore former, and I put this over here, and there's a bacillus species. There's a bacillus term for rod, but there's also a bacillus species that makes spores, and that's a spore. If a cell is dying, some species can make these spores, and they're very resistant. They're dormant structures, and they're hard to kill. In fact, you usually can't kill those with cleaners. There are some that you can, but you can't really use that cleaner on a table. So you're kind of wiping spores off. So those are things you have to consider. Quantity of organism to be destroyed if you knew you had a pretty hefty treatment to start with. The length of time and any kind of packaging. So basically just anything you would consider before you take a flamethrower to something or you're going to heat it up, you got to consider these things. So these terms: sterilization, removal of all living organisms, including spore formers, or what are called, they're actually called endospores. I don't have that here, but endo means within. But eventually the cell will fall off and the spore will just be there. Disinfection is a treatment used on inanimate objects, tables, chairs, things that are not living. Antisepsis or antiseptics are used on living tissue. And denaturation is a process where proteins are altered and it kills cells, and that's what heat does. How does heat kill microbes? It heats up the cell, it denatures the proteins, it changes their shape, and the cell can't survive. Okay, so heat is the most effective of all physical means. Now, dry heat, doing this right here, this incinerating, is the quickest, most efficient way to sterilize something. The problem is very few things can take direct heat. Metal can, but anything else really cannot. Moist heat is using an autoclave. I posted a video under the lab video tab. The second video shows, it's really short on how an autoclave works. An autoclave, you fill it with water. This looks a lot like the one we have in the micro lab. You put water in a basin on the bottom. You have a setting, it's 121, 15, 15. So you're going to put something in here, you close the door, and not everything can be autoclaved. Anything that can melt, you don't want to put in an autoclave. But what the autoclave does is it heats up 121 degrees Celsius, which is really hot. That's 200 plus degrees Fahrenheit. The water inside turns to steam. There is pressure, 15 psi, and the pressure forces the steam inside the cell, and it kills anything. So it's very efficient at sterilizing. These two terms kind of relate to this. There's a term called the thermal death point. The lowest temperature required to sterilize a standard quantity of pure culture within 10 minutes, and that's a temperature setting. Thermal death time is the time required to sterilize the culture at a particular temperature. Now, the ones that deal with this are mainly people that package, well, anything, but packaging food, you want to make sure you can heat something up without destroying it, but have it still kill microbes. So just be familiar with these two terms. Okay, here's our first lab scenario. Just imagine that you have a broth tube, a broth culture. In fact, I can kind of skip down here. So this is how you can tell for growth in a broth culture. Turbidity means it's kind of cloudy. If you shake it around, you can see it on the inside. There's some sediment at the bottom. This is a broth tube that has growth. This is one that does not have growth. See how it's clear. It's not as dense. So for this exercise up here, pretend you have a broth culture, and you're going to do a test to see, does flaming work? Does this part right here, does that actually work in killing microbes? Now, what we do in the past, we've used Bacillus. Now, that's actually a genus. Bacillus cereus, Bacillus subtilis, they are spore formers. So if you have a culture that's old, it's run out of oxygen and food, and it's formed some spores, it can be really hard to kill. So this exercise, you would do some aseptic technique first. You would take a loop. You would take your Bacillus broth culture. You would sterilize the loop. You would heat the barrel, aseptic technique. You would then take some culture out on your loop. You would heat the barrel of the tube again, put the lid on it, and put the tube away. You would then pick up the bottom of this plate, and you would do a simple streak on this side, just like you're supposed to. Normal aseptic technique, the goal would be to get growth of microbes on your agar plate. That's the part one of this exercise. It says label one side flame to one side control. This was the control side. You're just wanting to see if you have an organism that can grow. Okay, the next part, so you would streak this side first. The next part, you would take the same culture of Bacillus. You would get some culture on your loop. Same thing. You might do aseptic technique, heat the barrel, get some culture. But before you streak the plate, you would stick the loop into a flame and burn it first. Then you can see where the loop passed here. See the lines? Then streak the other side. This is called the flame side. You have now fried the microbes. You put them on a plate, and you can see nothing survived. So whoever did this did it perfect. This is good aseptic technique over here. And then, yes, flaming is very efficient at killing bacteria. You can see that. All right, the next exercise, Otto Claiming. Now, what you do beforehand is you grow a Staphylococcus aureus bacteria in a broth culture and a Bacillus. You leave the Bacillus out for a few days, let it start starving, so it'll form some spores. But now you have two cultures that are growing in a broth. They would look something like this. You can see the sediment at the bottom, turbidity. You have broth cultures. You would then take those cultures. When you go to do this experiment, you would then put them in an autoclave. So you're going to put them back into the thing we were talking about earlier, one of these things. And you do it for the proper time. 121, 15 psi for 15 minutes. 121 Celsius is very hot. 37 to 38 degrees Celsius is about 100 degrees Fahrenheit. So a summer day. So if you want to know how hot that is. You would nuke these cultures, okay, and then while you're doing that, you would procure 2 sterile broth tubes here. Once these have been put in the autoclaved and it's cooled off, you would then take about 2 loopfuls out of each culture, 2 from the Bacillus, You would then transfer those to a sterile broth using your aseptic technique. You would take 2 loopfuls out of the staph, same thing, using aseptic technique, and put them in a sterile broth tube. And then you'd put them in an incubator and let them grow 24 to 48 hours, like it says there. Well, and it says here, bacillus could be at room temp. We used to put those in the incubator. That's not important. So what we did is we had a culture with living organisms. We autoclaved it, and now we're going to see, did the autoclave kill everything inside the culture? And this is what it would look like. See, here is a culture that has living organisms. Once you put it in the incubator, it stays 24, 48 hours. It's going to be cloudy, have some sediment in there. If you flop it around left or right, you can see the turbidity inside. These are both sterile. And that's what happens. When you do this experiment, the autoclaving wipes out the broth culture. So it kills the cells. So then when you transfer those cells into a sterile broth and try to grow them in an incubator, they're already dead because they got killed by the autoclave. And it works very well, trust me. I used to be the lab person at Howard College, and I accidentally nuked all of our organisms one day in the autoclave, and it killed every single one of them, and we had to order new ones. So it works very well. So which culture was killed by autoclaving? Well, both. Even though bacillus is a spore former, it is resistant. Autoclaving kills it and uses extreme temperature and steam to force the heat inside the cells, and it will kill spores as well because of that. Okay, I'll start here next on the next video.